system, then you need to introduce a gauge field because the two are connected, right? The one source is the other. Same reasoning, if you want an independent spin current, then you need something independent, a geometric object that independently sources it. So, and I think Einstein-Cartan would be a formulation where you could do that.
Okay, thank you.
Okay, yeah. So with that, we are in time to begin with EmilHave's talk. Thank you very much for being here and giving a talk, and the screen is yours.
Okay, thank you very much for the introduction and the opportunity to give a talk here. So yeah, I will be speaking about Newton-Cartan submanifolds and fluid membranes. This is based on a paper that came out last year, which was done in collaboration with Jay Armas, who's at the University of Amsterdam, my supervisor, Jelle Hartang, who gave a talk here at HoloTube not so long ago, and Bjarke Frost Nielsen and Niels Opers, who are both at the Niels Bohr Institute. So let me begin by giving some background. So Newton-Cartan geometry was originally developed by Cartan in the 1920s to provide a geometric framework for Newtonian gravity in much the same way as pseudo-Riemannian geometry provides a framework for general relativity. And the way that you should think about Newton-Cartan geometry is sometimes like this bread here. So imagine that each slice of bread corresponds to a sort of a kind of spatial geometry, right? So in each slice you have a kind of, kind of space. This is a slice of space. And then each slice of space corresponds to an instance of time. So you have, in all reasonable incarnations of Newton-Cartan, you have this slicing of your geometry. And although it was originally developed in the context of Newtonian gravity quite some time ago, it has recently found applications in high energy theory in the context of non-ADS holography and in string theory and in something that was developed recently, which actually turns out to involve a subtly different version of Newton-Cartan to what we will present here. But yeah, so this is this non-relativistic gravity, which came out, it was a big paper earlier this year. Within the condensed matter community, Son has used this formalism as a background geometry to which you can couple field theories. And that approach allows you to extract currents and other sort of relevant objects that you wish to. So, for example, you get things like the Hall viscosity out of this procedure. What we've done is that we've sort of extended the realm of applicability of Newton-Cartan geometry to now include condensed, soft condensed matter, more specifically biophysical membranes, fluid membranes, actually, as we will see, which of course includes things like red blood cells. So the outline of the talk is as follows. So I'll begin by giving you a few more details about Newton-Cartan geometry and about submanifolds. Then I will talk about extremal Newton-Cartan submanifolds, which are nothing but submanifolds that arise as solutions to equations of motion that we get from actions. And of course, in order to get such equations, we'll need to have a proper variation framework. And then finally, I'll say a few words about how this actually has applications in soft condensed matter. Right, so torsional Newton-Cartan geometry consists of a manifold M along with a so-called Newton-Cartan structure. So this is this triplet here. So the triplet consists of a one-form tau mu, which is called the clock form, and a symmetric covariant 2 tensor of co-rank 1. So it has a 0 eigenvalue, which you should think of as a kind of spatial, it's not a metric, but it's an object that measures space. So it's a kind of a ruler, right? So similar to the bread we had on the previous page, a Newton-Cartan geometry usually has a slicing like this in terms of temporal hypersurfaces. And if we zoom in, the thing that measures the space on each temporal hypersurface is this h mu nu. The final ingredient is this M field here. This is the Barkman mass. This is Barkman. And this is the field. So if you consider a field theory living on a Newton-Cartan background, this is the field that couples to the mass current. Now, along with these objects, we can define not exactly inverses, but sometimes they're called projective inverses, such that these relations down here are satisfied. So that sort of is what replaces the good old G mu nu. G mu nu is, well, G mu, you know, the usual completeness relation for a pseudo-Riemannian metric is replaced by this set of relations here. Now, an important point to note is that the torsion is intimately related to the properties of the clock form. More specifically, depending on the properties of the clock form, we can classify different notions of Newton-Cartan geometry. So the most general notion is the torsional Newton-Cartan, where there are no constraints on the clock form. This turns out, however, to be acausal. So it is not particularly physically relevant. The next version is this twistless torsional Newton-Cartan, where the clock form satisfies the Frobenius integrability condition, leading to this slicing that we saw in the previous slides, where you have hypersurfaces of absolute simultaneity, and the most restrictive version is just called Newton-Cartan, which has a closed clock form, because we will only work very locally, we will take this to be equivalent to the clock form being exact. So that means that we can write tau as the d of some t, which expresses some kind of global notion of time. A very useful perspective to take in the context of Newton-Cartan geometry is actually that of a gauging of an algebra. In this case, the Barkman algebra, which is the centrally extended Galilean algebra. So it contains a central element, which is precisely, so this is it has a central element usually denoted as M, and this is precisely what corresponds to the M mu field that we saw as part of the Newton-Cartan structure on the previous slide. And since these will feature extensively in what is to follow, I just here make a small point out of telling you that you can, this Barkman algebra contains Galilean boosts. So these are transformations of this form, where you transform the spatial field like this, so where Vi is to be thought of as some kind of velocity. The objects H and M and V are themselves not invariant under boosts. So it's very useful to define these objects H hat and H bar and V hat, which are invariant under boosts. So this is just for you to know what those objects are. Now, when it comes to submanifolds, the notion of a manifold, of course, does not change whether we put a Newton-Cartan structure or a more familiar metric on it. So the notion of submanifolds itself is, of course, identical, right? So if we coordinatize our submanifold sigma in terms of these sigma a's here, then we can specify an embedding by providing a set of embedding maps, such that if we coordinatize our manifold M with x mu, then set these embedding maps equal to these coordinates, we get the location of our submanifold. These embedding maps lead to what we call tangent vectors, which are just the pullback maps that can be used to pull back objects in the ambient space to objects on the surface, and a set of normal vectors that are orthogonal to these tangents. And this furthermore allows us to define kind of inverse tangents and normal vectors rather than the normal one forms that satisfy this completeness relation here. Now, since there is no notion of raising and lowering indices in Newton-Cartan geometry, you have to be a little bit careful. But these objects, so these are not directly related to these, but rather are implicitly defined via this relation here. So in particular, they are not unique. And this will then allow us to define what we mean by time-like submanifolds, which are submanifolds which include the time direction, so to speak, so that the tau is fully contained within the submanifold. So in particular, this means that the normal projection of tau vanishes, or that the normal one form is entirely spatial, in the sense that if we raise the index, we get the normal vector, but you should be, again, careful because it's a one-way street. You cannot go back to the normal one form once you've raised the index. And to illustrate this, we have this figure here just to sort of say that if you have this surface here, then the normal is at all time, this is the normal vector, so this is at all times orthogonal the time here, right? So if it's sort of bended in the time direction, we would have a sort of a scenario here where there would be a component in the time direction, right? And we don't want that. So that is sort of what we mean by a time-like submanifold. Now, an interesting property, which is novel in this scenario, is that in contrast to Riemannian geometry or pseudo-Riemannian geometry, the induced structure on your Newton-Cartan submanifold is not the pullback of the ambient Newton-Cartan structure. So you see here that the novelty consists in the fact that the normal projection of this inverse time-like field lines, which is sometimes known as the Newton-Cartan velocity, appears and spoils the relation that the induced structure is identical to the pullback. So from a mathematical perspective, that is sort of interesting. And the interpretation of this field as the linear velocity of the submanifold were sort of with respect to the ambient space. But because we will consider things that are anyway boost invariant, this will not have a huge bearing on the physical systems that we will examine. But this is just to sort of tell you a little bit about the interesting properties of the geometry that we have developed. Okay, coming on now to the variation of framework and the extremal submanifolds and the equations of motion. We first need, of course, a notion of an action functional. But before we discuss that, there is an important point about setting the torsion to 0. So we will be considering torsion-free actions and torsion-free geometries. Now, the important point here is that the variations that we're interested in are variations with respect to the embedding map X here. So think of this as some kind of generalization of the Nambu-Goto action. Now, these variations turn out to be equivalent to a certain class of diffeomorphisms. And since those diffeomorphism variations are expressible as a Lie derivative, using the fact that Lie derivatives and exterior derivatives commute, this is known as Cartan's formula, or it's a consequence of it, if you like, then it does not actually matter whether we set the torsion equal to 0 before or after we perform this variation. So in general, it is not true that you can set the torsion equal to 0 before variation, but because all we're interested in are the variations with respect to the embedding map, this can actually be done. So that is a hugely simplifying feature. Now, the way that the action functional depends on the embedding map goes via these fields here. Right, so this is a bona fide pullback, while and so is this h bar actually, right? Because recall this was a boost invariant quantity. The last object that our action depends on is the extrinsic curvature, right? So recall that this is sort of a measure of how much your surface curves, so your embedded object, how much that curves in the ambient space. So more sort of precisely, you can think of it as how much the normal vector varies from one point to another, right? So if you have a very curved surface, the normal vector will vary hugely from one point to another in the ambient space when you go along the surface. So since we consider action functionals of this form, the variation takes this very general form. So to each of these objects, once we vary it, we can associate some kind of current. So the variation of the clock form leads to an associated response that we call the energy current, while the response to this h bar thing, which of course, as you recall, you could write this out in terms of delta tau A, delta H check AB, and delta M check A if you wanted, because recall that this object consisted of all these objects. And precisely because it also contains this mass gauge field. This is known as the Cauchy stress mass tensor, and sort of is a generalization of the energy momentum tensor, if you like. So you can combine these two objects actually into an energy momentum tensor. And then finally, the response to a variation in the extrinsic curvature is the bending moment. So if you bend your, so recall that this K was really a measure of how much our surface bent, it makes sense. So the associated response will keep track of that and is known as the bending moment. Now, if we perform these variations, what we get are with respect to the embedding map So we compute the equations of motion with respect to embedding fields. The resulting equation should be thought of as, in some sense, a generalization of Newton's second law. So computing the variation, we get a set of equations of motion indexed by mu, right? We get one for each field x, each embedding map here. And this we can then project both along the surface and orthogonal to the surface. If we project along the surface, since we have this correspondence between embedding map variations and diffeomorphisms, it's easy to see that if we project along the surface, we will get some kind of diffeomorphism word identity, which is identically satisfied for the class of actions that we construct and the ones that we saw on the previous slide. And that is, you can reduce this to some sort of, you know, this is, if you want to think about it in terms of Newton's second law, this is just a statement of mass conservation. So this is the same as saying that the mass does not depend on time. While the orthogonal projection leads to the so-called shape equation. And this is really a force balance equation. So on the right-hand side here, what you see is that the generalization of mass is this stress mass tensor, while the generalization of the acceleration is how much your surface bends. And of course, on the left-hand side, you have this rather complicated expression, but this is sort of some given force that acts on your membrane. And this is known as the shape equation, and it's sort of a very famous equation in the context of membranes. But what is important to keep in mind here is that using Newton-Cartan geometry, this has time components. So this, and it incorporates time in a covariant way. So this is something that did not exist before, although the sort of form of the equation is similar to the one without time in some sense. Now, another very important aspect of using Newton-Cartan geometry is that precisely because we have this geometric formulation, we can apply the techniques of equilibrium partition functions or hydrostatic partition functions, if you prefer. In this approach, what you really do is that you geometrize local thermodynamics. So concretely in this context, equilibrium sort of corresponds to the existence of a set of symmetry parameters, which generalizes the notion of a killing vector. And these preserve the Newton-Cartan structure in the same way as a killing vector preserves the metric in pseudo-Riemannian geometry. And in particular, for our purposes, such a set of symmetry parameters is taken to exist also on the surface itself. So rather than a mu index here, we'd have a Ka and a lambda mu k check, sorry, not mu, but rather A, and a big lambda check K. So this is a Newton-Cartan killing vector. This is a symmetry parameter for the boosts, and this thing here is a symmetry parameter for the gauge transformations of the mass gauge field that we talked about earlier. So this is the symmetry parameters of the geometry, which we then, in this equilibrium partition function approach, convert into local thermodynamic data. So we do the usual thing. We construct a free energy by Wick rotating our action and compactifying the time with period 1 over T0, where T0 is some global temperature. And then we map the geometry to thermodynamics via these relations here. So we get a local temperature and a local chemical potential and a local fluid velocity along our membrane, right? So all these things are on our membrane that we embed in the ambient space. So this really constructs us a notion of fluid membrane that comes from an action. And the simplest avatar of this free energy is the soap bubble action, where we only have a surface tension that then depends on the local thermodynamic variables, and via those on the geometry. So this is this action here. And you can show that it describes soap bubbles. Now, one other interesting consequence of using Newton-Cartan geometry is that you can really talk about the waves in the fluid here. So if we consider a trivially embedded thin fluid sheet, so it has topology R2 cross S, I guess, because we compactified the time. And you put a fluid on this, which is at rest, so it only has a time component. What you can do is that you can find the shape equation, right? So remember the shape equation was m times a. So this thing here, so those two equal to 0 is really the shape equation, because we have this surface tension model above, which did not depend on the extrinsic curvature. If you then fluctuate this equation along the orthogonal direction, right? So you make some wave, you fluctuate your sheet, your fluid sheet. And what you get is a wave equation of this form here, which gives rise to a dispersion relation, as shown here. And this really is the classic Landau-Lifshitz result from, for the dispersion of elastic waves and thin elastic sheets. And this really, is only possible because we used a Newton-Cartan formalism. At least you can get it in other ways, but geometrically, this is shows us the power of using this fully covariant method. So, coming to perhaps a slightly more interesting model, not just the surface tension model, we can consider the so-called Canham-Helfrich model, which was developed in the 70s and famously includes red blood cells as one of its solutions. Or, when I say red blood cells, I really mean that the shape of a red blood cell solves the equations of motion that we get from the free energy that has this form. So it depends on a series of constants. So this is the surface tension as before, but is now a constant. So in particular, there is no notion of local thermodynamics. You have no fluid on your shapes. You just have shapes. And K here is the trace of the extrinsic curvature. Some of the interesting solutions to this model include the so-called spherical vesicles. So these are just S2s. And they are realized in nature, in biological system, as for example, liposomes that turn out to be important for the delivery of drugs. Another interesting class of solutions are the two torus, which were actually only observed in 91, right? So these tori were observed in 91, and it turns out to get those toroidal vesicles, you need to do something special to phospholipids, and they don't have any biological relevance per se, but they do form under certain conditions in the laboratory. And then finally, and famously, you have this biconcave discoid, as it's called, which is the red blood cells shape that the Canham-Helfrich model is most famous for reproducing. But what we can do is that we can make these into fluid membranes using our more elaborate approach using equilibrium partition functions. And in this case, the material constants are promoted to material coefficients that really depend on the local thermodynamic variables. And in this case, our proposed generalization of the Canham-Helfrich model has this form here. And of particular note is this A3 term here. So before, if you recall, there was only, you had something like C0 plus K squared. So you only had K squared term in the other Canham-Helfrich model. You didn't have this K dot K. And K dot K is, in this case, it's HAB, HCD, HACKABD, right? So it's the combinations of K's and H, which is not just the trace squared. So usually these are actually related. So when these constants are, when these coefficients are constants, these two terms are related by the Gauss-Kodachi equations. Once these terms depend on the geometry, that is no longer true, and you get a sort of a new term that splits away from the K squared term. And this, of course, reduces to the Canham-Helfrich model for if you set these equal to certain constants. So the map is given here, although it's not necessarily particularly important what the exact map is. But of course, what we can do is that we can compute, for example, the bending moment and the stress mass tensor as we saw before. And the bending moment in particular turns out to be related to some kind of generalized Young modulus. But the precise details have not been worked out yet, and we don't exactly know what the biological implications of having fluid membranes rather than just a fixed geometric structure, what those implications are. So it will be very interesting to, for example, work out what novel effects this A3 term will have, as well as, from a purely effective field theory point of view, you could actually add additional terms to this free energy that we had on the previous slide, such as this one here. And that would be interesting to see what consequences that would have. We could also think about generalizing this thing that we did for the thin elastic sheet and consider small fluctuations in the more general Canham-Helfrich model and see what kind of dispersions we'd get. That would tell us something about the stability of such vesicles. More ambitiously, perhaps, we could also sort of aim high and seek a fully out of equilibrium description using something like Swinger-Keldysh, which so actually very recently, not I think like 1 month ago, there was a nice paper about how to implement Swinger-Keldysh in a Galilean context. And also maybe not of any particular biological interest, but more from a mathematical point of view, it would be interesting to also develop this notion of submanifolds for other non-Lorentzian geometries, such as, for example, Aristotelian geometry, where this VI that I briefly talked about, so the normal projection of this inverse time-like field bind, should perhaps play a more prominent role, because in Aristotelian geometry, there is no boost invariance. But those are all left for the future. And with that, I would like to thank you for your attention and invite you to ask questions if you have any.
Thank you very much, Emil, for your very nice talk. Do we have questions before I ask? Anyone? I can start. I'm curious, so let me begin with a question that was just me not understanding. Could you go back to the relation between the torsion and the clock form that you had on one of your earliest slides?
So this one, you mean?
I think even earlier, slide 5 or so. Yeah, right here.
Yeah.
Could you say again how those two are related?
Yeah, so that is indeed. So that's a very good question, because it is indeed not obvious from the from what we have here. So what you have to do is that you have to write down connections to see that this is in fact related to the torsion. So if you write down a connection, you will find that the connection has a form. So the connection that you can write down is something like this. So you can write down, so based on this gauging of the Barkman algebra, you can you get a bunch of connections that you can then combine into something that you could think of as the generalization of the Levi-Civita connection. Mm-hmm. And that precisely involves, so you can write it like this, plus something that involves the H's. So here you get something that looks a little bit like the Levi-Civita connection in terms of H bar, but the important part is this first part here. Mm-hmm. This is a, I mean, there are many choices for the connections, but common to all of them is that they will have torsion. So you see that if you take the torsion here, you get something like, so if you compute this thing here, this denotes anti-symmetrization. You get this thing here. Right, so this of course is, these are the components of the exterior derivative of tau. Right, so this is a 2 form, and it's known as a torsion 2 form. Mm-hmm, mm-hmm.
I see. Go ahead. Sorry, I didn't want to cut you.
No. Yeah, I don't have. So this is the relation between tau and torsion, and this.
So this is there because you now have a vector at your disposal as opposed to having only a symmetric metric in GR.
Yeah, exactly. So you now have a one form which tells you how to measure time. So if you integrate this clock form along a path in your manifold, this is what will give you the time.
Could you remind me what the mu is?
Yes. So exactly, indeed, that is a good question. So this is an extra gauge field we take to be part of geometry, and the role of this gauge field is, so there are many ways to think about it. So from a algebraic perspective, it corresponds to this central element in the Barkman algebra. So if you gauge it, this algebra, then what you do is that you associate to each generator a gauge field. So you write down a general connection on this algebra, some a mu, and then that is a sum over sort of gauge field times generator. So in particular, you'll have something like m mu plus everything else. So that is one way to see it. And the role of this gauge field is to introduce a notion of mass. So, for example, if you look at a free particle, so you go to flat space and you just look at a free particle in a sort of classical analytical mechanics approach, what you find is that if you compute another charge for this Lagrangian, you will see that first of all, if you perform a Galilean boosts of this kind here, you will find that the Lagrangian transforms as a total derivative. And you will find that the Poisson bracket between a boost and a momentum will actually involve the m. And via the standard identification between Poisson brackets and algebras, you will see that in order to actually have massive representations, you need an extra m field in this Barkman algebra.
Okay, yeah. It's a central charge, right?
This is from the perspective of the algebra, it's a central charge.
Okay.
Or central element, if you like.
Okay. First, thank you, and then any other questions? Anyone?
I do have a small one, if possible.
Sure.
So could you go to the slide with Newton's image? Picture. I don't remember which one. Yeah, precisely. So maybe you say that and I missed it, but if it's not too complicated, could you tell me what is curly D object with 3 indices that you define in the F equals MA analog?
Yes, absolutely. So you mean this thing here, right?
Yeah, precisely.
Exactly. So this is the response to the variation of the extrinsic curvature. So it's
okay, you said it there. Yeah, I miss it.
Right. Yeah. No, but maybe I went too fast.
Okay,
so this is the response to varying the extrinsic curvature. So it tells you about. So it's the response to a change in the bending of the membrane.
Okay. Thank you.
Yeah, you're welcome.
Any other questions? Okay, I have one comment and one suggestion. If there's no other questions, then one comment is that maybe Rajiv and you could talk to each other, because Rajiv, if I understand correctly, then you're looking for the relativistic version of exactly pretty much what's on the screen right now, right? A generating function that tells you what couples to what and how you can get spin into the game. And so I think that might be a good, you would have to do Einstein-Cartan, not Newton-Cartan. But
sure.
Like since you guys have the knowledge, and I see that Jelle and Niels are here as well. So maybe you guys want to jump on this and help with this.
Oh, sure. So one comment I can say is that the relativistic version of this has been worked out by Jay, so Jay Armas. He has, and this includes all conceivable couplings to spin, to spin connections, and almost all conceivable things.
So
Daniels, go ahead.
No, so I just want but So hi, Matthias. First of all, nice to see you. This sounds interesting, but and maybe there's still something to do and explain. But just to underscore what Emil said, there are 2 or 3 or more papers by Jay and also by Akash, where they have developed this precisely for the relativistic case in great detail. This effective theory, including all possible couplings to spin and bending moments.
Mm-hmm.
But okay, this is not to say that we're not interested in talking, but there's already something to build on.
Mm-hmm. Maybe to apply that might be helpful, because often the problem is that the experts lose interest once they understood the theoretical side, and then if somebody comes along and wants to apply it to, let's say, forming, like writing down hydrodynamic description of a system with spin or so, then like all that knowledge has to be somehow transferred.
Yeah. Exactly. No, so that's where interaction is super good, rather than letting people chew on long papers with whole formalism. So, but Jelle, sorry to interrupt you.
No. So hi as well, Matthias.
Hi.
I just wanted to make the remark that the relativistic version and the version that Emil presented, they are related by this thing called null reduction. So if you have the relativistic answer, you can just null reduce that, and that gives you the Galilean answer in a sense. So it's always interesting to do that, because you learn something about the non-relativistic version of the theory.
Mm-hmm. Yeah, thank you. That's really good comments. So do we have any other comments that were spawned by this? If not, then we can close this session. I'll stop the recording. And if anybody wants to stay around and chat a bit, or exchange numbers or whatever, then please go ahead. I'll just stop the recording now.